A Roman bishop sits in the window of his episcopal home on the North African coast. It is late afternoon. He looks out at the sun setting over the Mediterranean and watches the waves break along the shore, sand piling into disordered heaps. When the sun sets, it will be time to light the lamps if he wants to continue his work. He is Augustine of Hippo, theologian, philosopher, and saint, famed for his 5 million words of writing that have survived to the modern age. He longs for the golden light to remain, for time to pause or even run backwards. What might that look like, he considers. The sun would rise from the horizon, not so different to the glory of a dawn. But all else would seem very strange. The waves crashing on the beach must collect and assemble themselves in a most unnatural fashion, with water droplets rising towards one another into a teetering pile before retreating back out to sea. It seems to violate the Lord's natural order, and Augustine shies away from the discomforting thought. What then, if he could witness time laid out before him, moving forward inexorably, from one moment to the next? The waves would crash unceasingly on the shore, advancing on the bustling town until it reduced his home to little more than a heap of rubble and sand. As his quill drips ink onto the parchment, Augustine's mind wanders to see time itself advancing, ruining all in its path, spreading its relentless chaos. The present world of man crumbles to meaningless piles. The thriving natural world eventually decays to nothing more than dust in the wind. And in the sky, stars wink out one by one, until there is nothing left by which to measure the passing moments. With nothing more for time to devour, would this finally be the end of the voracious beast itself? What then is time, if not the inevitable march of disorder, the inevitable destruction of God's structured universe into nothing more than an eternal pile of sand? Shaking himself from the darkness of his waking dream, Augustine finds it truly is darkening outside. With the last glimmers of the setting sun, he breathes deeply and scratches out his final words for the day. What then is time? But had Augustine really been able to see into the future and probe the minds of modern scholars, he would have seen that his dark imaginings were not only accurate, but substantiated by the highest theoretical physics and cosmology. The hungry beast of time, powered by ever-growing entropy, is unstoppable and relentless. It is driven not by some demon bent on destruction, but by the unassailable forces of mathematics that have gripped the cosmos from its first moments to its inevitable end. This entropy, bound up in the mathematics of particles and energy, powers the arrow of time, forcing our eyes forward into a future that is unavoidable as it is disturbing, and a past that is forever just out of reach. Some 1.5 millennia after St. Augustine found his words lacking on the subject of time, the industrial English city of Manchester was preparing to manipulate it. In the early 19th century, timekeeping clocks were calibrated against local sundials, giving rise to times that could differ by as much as 30 minutes between the west and east coasts of England. But with the advent of the Industrial Revolution and the spread of the railway network, the country suddenly needed a unified system. Now, the difference of a few minutes between London and other stations on the network could mean passengers missing their trains or even collisions on intersecting tracks. And so, it was decided that, for the first time in history, time itself would be changed. In January 1846, the residents of Manchester collectively travelled through time, jumping 13 minutes in an instant as the town's clocks were adjusted to match the standard time set by the Royal Observatory in Greenwich, London. Although time had been measured for millennia following the passage of the sun across the sky, this was the first time it had been standardized, thanks to the incessant march of industry. But in truth, this so-called standard time is arbitrary, little more than an imaginary structure for our busy lives. The sun still sets in Manchester 13 minutes later than in London, regardless of the time on the clocks. And yet the steam-powered locomotives of the Industrial Revolution did open our minds to the nature of time in an altogether unexpected way. Some 20 years before England's clocks bent to the unstoppable force of the railway, efforts to understand the heat engines that powered these mechanical juggernauts led French engineer and physicist Sadi Carnot to make a prophetic observation. Steam engines had been quickly adopted across the rapidly industrializing world, bringing success and riches to all who embraced them. But little work had been done to understand how they really worked. This was the concern of Carnot when in 1824 he penned his influential Reflections on the Motive Power of Fire. His observation, which may seem simple and obvious now, was that heat always flows from a warmer body to a colder one. This explains how a fireplace can warm a cold room, why ice cubes melt when they're left in the sun, and why molten, newly formed planets solidify and cool in the cold vacuum of space. It is an irreversible natural process, and it is this that provides the motive power in all heat engines. In this, Carnot laid the foundation for the theory that was to become the second law of thermodynamics. This law was developed over the following century until it was brought in line with our evolving physical frameworks. Now, we recognize that not just heat, but all systems move in a single direction, one that will decrease the free energy of that system. Today, we describe this change in terms of entropy, a mathematical way of measuring the amount of disorder within a system. Specifically, it measures the number of possible ways that a large-scale, macroscopic structure can be created from its microscopic components. A train locomotive is a highly ordered structure. There are very few ways of arranging all the component parts to create a functioning engine, and so we say that its entropy, its measure of disorder, is low. A heap of wreckage in a railway scrapyard may have the same components as the locomotive, but piled on top of one another in a disordered heap. There are many ways of arranging the scrap to make the same chaotic pile. Because of these many possibilities, its entropy is by definition high. What's more, entropy always tends to increase. A functioning train locomotive, if left for long enough, will always become a disordered pile of wreckage. The chances that a heap of engine components will spontaneously group together and assemble into a fully functioning train are infinitesimally small. Entropy always increases. Everything tends towards disorder. So when coal burns in the locomotive engine, it changes irreversibly from a structured lump of energy-rich carbon to a disordered pile of inert ash, while its free energy is dissipated into the engine's boiler as heat. This fundamental property of our universe is not only the reason for steam power's success, but also the basis for all of time itself. This unstoppable change in entropy in everything around us provides us with a way of distinguishing one moment from the next. It was just past dawn when Arthur Eddington began walking home through the streets of Cambridge. He'd spent the night peering up at the stars from the university's observatory, and his head was still filled with wheeling points of light as he tried to make sense of their celestial motions. Suddenly, he was pulled sharply out of his musing not far from the door to his apartment, as a stern-faced woman resolutely blocked his path. She held out a white feather, its soft, downy barbs catching in the morning breeze. He knew better than to resist. Taking the feather, he smiled politely and neatly sidestepped her. Moments later, just inside his home, Eddington shook off his coat, hung up his hat, and added the feather to the growing pile on the mantelpiece. It was 1917, and Arthur Eddington was a Quaker and a pacifist. According to society, that made him a coward. But Eddington was no coward when it came to grappling with the mysteries of the cosmos. He became a world leader in gravity and relativity. In 1928, he wrote an ambitious book that made the concept of entropy accessible to the layman for the first time. In it, he asked the reader to imagine the universal increase in entropy as an arrow, which can only ever point from order to disorder, from the past to the future. In this, he laid the foundation for the arrow of time, defined by the directional change in entropy from one moment to the next. As time moves forward, things become more disordered, and the passage of time is represented by this inescapable growth in cosmological chaos. The arrow of time thus describes why time must always move forward, why cause must precede effect, and why we can only ever experience it in that way. Time travel has become an immensely popular trope in science fiction, bending our minds with the paradoxes it creates. To travel backward in time, one must experience the universe in the unsettling improbability of decreasing entropy, of things spontaneously becoming more ordered. Waves uncrashing on a beach and backing away from shore, and heaps of wreckage self-assembling into functioning engines. Not only does it seem unnatural, but it violates the arrow of time that rules the universe and our own experiences. Even if one travels instantaneously backwards and then continues to experience time forwards from a point in the past, it becomes impossible to define a consistent, universal arrow of time. Theoretically, if we could find a way to travel faster than the speed of light, then through the mind-bending relationship between space and time, we would also be moving backwards in time. So says the mathematics, at least, but the reality is quite different. The speed of light is one of the most reliable, unassailable constants in the universe today. When we travel at the speed of light, Einstein's equations of relativity tell us that our mass rises to infinity, while our size shrinks to zero. Surpassing that breaks every law of physics we know of. Not only that, but by jetting into space faster than light and backwards in time, we would arrive at our destination before we had departed. We become trapped in a causal loop, isolated from the normal universe where, thanks to the arrow of time, a cause must always precede the effect. Stephen Hawking was so certain that reverse time travel would not be possible that he held a party on the 28th of June, 2009, for which he only issued invitations the following day. The only way a guest could attend was if they travelled backward in time. Nobody made it, and Hawking was left alone with 10 bottles of champagne. Travelling forward in time is another matter. It's easy. We do it all the time, experiencing 1 second of the universe for every second of our lives. We can even do it at an accelerated pace if we stray too close to a black hole and are gripped by the space-time altering forces of its enormous gravity. Skirting close to the event horizon of a rotating black hole about 8 times as massive as our Sun, we can zoom forwards in time 60,000 times faster than our companions on Earth. We can jump forward 17 Earth hours in a single second of our own lives. The arrow of time dictates only the direction, not the speeds that one may travel. This directionality, sometimes called non-symmetricality of time, is an oddity that sits in contrast to most other physical laws within our cosmos. For example, gravitational attraction looks the same wherever or whenever you happen to observe it, and two particles in a gas behave almost like solid steel balls, conserving their energy and speed as they collide and rebound. These collisions would look the same whether played forward or in reverse. Thus, the arrow of time does not result from the movements of individual particles, as these are governed exclusively by the symmetrical laws of physics. The increase in entropy and the passage of time is not an inevitable consequence of our known physical laws, but it is an inescapable feature of the universe we inhabit. Reconciling these two facts remains one of the great unanswered problems in physics. Some have even suggested that the very existence of time is an illusion, a consequence of our inability to perceive the world in all its detail. In the early 19th century, French philosopher and physicist Pierre-Simon Laplace contemplated the existence of an omnipotent individual, a veritable demon, who could know the precise position and momentum of every atom within the universe, and thereby calculate the nature of the cosmos for any point in the future or past. Could Laplace's all-knowing demon ever really exist? The symmetrical natural laws of the universe suggest yes, but entropy and time suggest otherwise. The irreversibility of time, created by the dissipation of energy and the increase in disorder within a system, makes it impossible to make such rigid predictions about the past or the future. What's more, on the tiniest scale, the universe is ruled by quantum mechanics, whose central tenet is one of uncertainty and fluctuation. Quantum uncertainty means it is impossible for us to simultaneously know the position and speed of a single atom, let alone all of the atoms in the universe. If we could, then the entropic measure of disorder would cease to have any meaning. Entropy itself would not exist, and neither would time. But this doesn't address the question of why there is asymmetry in the first place. Modern scientists have suggested that our ability to draw the arrow of time is a result of our relative proximity to the Big Bang. Just as the concepts of up and down only have any meaning when close to the surface of the Earth, so it is our nearness, cosmologically speaking, to the beginning of the universe that allows us to orient ourselves in time. If that is the case, then the Big Bang must have represented a moment of extreme conditions, from which the universe is still winding down, nearly 14 billion years later. Ludwig Boltzmann never stayed in one place for very long. Throughout the late 19th century, he moved from post to post, in Vienna, in Graz in Austria, in Heidelberg in Germany, and in Berlin. In this, Boltzmann's personality mirrored the behavior of the atoms that he studied, always moving, never ceasing, filled with unpredictable energy that could fling him in one direction or the next, from exalted joy to suicidal depression. Yet his mood swings did little to dull his scientific fervour. He was a pioneer, ahead of his time in his atomic vision of the world, developing an entirely new field of science: statistical mechanics. With this, he created a framework to understand the unceasing growth of entropy for the first time. Simplistically, he imagined colliding particles as balls on a billiard table. The physics and geometry of the collisions are predictable, providing you know the speed and angle of impact, and the usual natural laws apply. But the more collisions there are, one after the other, the more disordered the table becomes. It becomes increasingly unlikely that the continuing collisions will result in an ordered pattern. Not impossible, but spectacularly unlikely. It might happen once, but to travel against the flow of time is asking it to keep happening, and is against all the odds. He argued that the second law of thermodynamics, and by extension the arrow of time, was a statistical necessity, a result of the fact that disordered states are much more likely than ordered ones, even in a world governed by uncaring, symmetrical, natural laws. Tragically, under a barrage of criticism for his mathematical treatment of existence, he committed suicide before his theories could be proved correct. Today, if we visualize the universe as an infinite billiard table, then the ever-growing entropy that defines the arrow of time shows that we are still within sight of the beginning of the game. The universe must have begun with a higher degree of order if we are still statistically approaching randomness. But, based on what we know about the earliest moments of the cosmos, this seems counterintuitive. A homogeneous soup of protons and raw energy at first glance seem much more random and disordered than the stars, galaxies and humans that exist today. How could a uniform universe have lower entropy than the organized one of the present? It is in fact possible to calculate the entropy of the early and modern universe, using the so-called Boltzmann constant. At the Big Bang, the entropy of the compressed, radiation-filled baby universe was by no means low. It was 10 to the power 88 times the Boltzmann constant, a 1 followed by 88 zeros. In contrast, the entropy of the universe today is a 1 followed by 103 zeros, some quadrillion times higher. So the entropy of the universe has indeed increased, but the starting point was not as low as we might imagine. It turns out that the order that we humans are so attuned to actually has very little impact on the overall entropy of the universe, and 14 billion years of time has barely changed the entropy of the background radiation that's been there since the beginning. Entropy has increased by a factor of a quadrillion because of the addition of one particular structure: black holes. These mysterious objects that reside at the center of galaxies and which are lurking darkly elsewhere throughout space are the result of vast amounts of matter being packed into a small space. They contain so much matter, so many particles, that there are almost limitless ways those particles can be arranged to still create the same massive, lightless hole in space. This alone is enough to make a significant impact on the entropy of the entire universe. The black hole at the center of the Milky Way galaxy alone has entropy that is 1,000 times greater than the entire universe just after the Big Bang. With time, natural physical laws of gravity will drive the creation of more black holes and cause existing ones to grow, driving the entropy of the cosmos ever higher and driving time's arrow forward relentlessly. But not, as you may think, forever. The heat death of the universe will see all energy evenly distributed across near infinite space. For now, entropy continues to increase inside black holes, and the disorder of the universe as a whole gradually grows as time's arrow flies ever forward. But one day, trillions of years from now, black holes will have swallowed every last particle in the cosmos, and they themselves will have evaporated away. Nothing can survive this inevitable end, when all energy and matter is no more. Overall, entropy will be as large as it is possible to be, a white noise of randomness in ultimate equilibrium. And since time cannot flow backwards, it will stay that way, forever. Without any change, time ceases to have meaning. This truly is the end for time. A cold, black, empty universe existing outside of time and space as we understand it. But it would be wrong to assume that nothing happens in this empty universe. Entropy might have reached its maximum value, but that only means that there are a near infinite number of ways that the universe can be arranged. The physical stuff of the universe can fluctuate through these random permutations, and so the entropic equilibrium is a dynamic one. The universe as a whole may not become any more ordered, but statistics suggest that small fluctuations could create pockets of organization at random. When tossing 100 coins, it's extremely unlikely that all will show tails. But it's not impossible. And since this most random universe at the end of its life is effectively eternal, there is plenty of opportunity for random tosses to give any result you can imagine. Modern physicist Sean Carroll has used this principle to write a potential origin story for our own cosmos. Suppose a universe has lived its life and met its entropic end many billions of years ago. The result would be an unchanging, timeless parent universe with random local fluctuations in entropy. One of these fluctuations might just configure its energy in such a way as to create a highly compressed pocket with inexplicably low entropy. A baby universe, with the billiard balls figuratively set, ready for the first break. This, Carroll argues, could be the beginning of our Big Bang, and the beginning of our arrow of time, created as a hiccup from a timeless parent. The idea seems compelling and seems to fit neatly with some cyclical origin stories. But it also raises a strange and disturbing possibility. An aged parent cosmos that can create an entirely new baby universe can also use its limitless coin tosses to create pretty much anything else we might imagine, including more of us. And new us, as opposed to entire universes, require far fewer coin tosses. More specifically, bodiless human brains drifting alone through space. This so-called Boltzmann brain, named after Boltzmann's work, is part of a thought experiment that looms over our current theories of eternal maximum entropy. It seems vanishingly unlikely that a cold, empty universe could create a human brain, replete with thoughts and artificial sensations and memories, but it truly is one of the permutations that the maximally disordered cosmos can cycle through. Given enough time, this seemingly impossible permutation could spontaneously appear. Given an even longer amount of time, it could happen over and over again. Given the eternal end to our universe, statistically speaking, Boltzmann brains are inevitable. And in fact, in purely statistical terms, actual humans, with the added complications of physical bodies existing in the actual universe when it is nearly 14 billion years old, are vastly less likely than Boltzmann brains in an empty universe that has been cycling through random permutations for hundreds of trillions of years. It follows that, statistically, our thoughts and experiences are much more likely to be an illusion of a fictitious universe conjured by non-corporeal Boltzmann brains than they are true reflections of the cosmos so close to its birth. Of course, physicists don't believe that this is really the case, and the goal of modern cosmology is to find a theory that does not threaten our existence and create a timeless eternity filled with dreaming horrors. If we really are here experiencing the universe at nearly 14 billion years old, then the idea that the universe will exist forever in timeless stasis must be wrong. We need a theory that will produce a definitive end to space-time before statistics has the opportunity to create Boltzmann brains to outnumber us. There are possibilities being actively pursued at the very bleeding edge of theoretical physics. A contracting universe that leads to a big crunch and rebirth, multidimensional string theory brain collisions wiping us out. The search continues in hope. And so, St. Augustine could not have known how right he was when he wrote that time evades definition. Arthur Eddington could describe the arrow of time, but he couldn't truly comprehend it. Boltzmann, for all his troubled brilliance, only created a statistical demon that continues to threaten our reality. And even today, modern physicists have no definitive explanation for the beginning or end of time. Which raises the grim thought. Perhaps all of these influential minds were really no more than that. Minds floating aimlessly through space, dreaming of a universe they could almost understand. And yet more likely, perhaps our own memory of these scholars is a fiction, concocted by our single Boltzmann brain, drifting in an eternal, timeless universe. Or perhaps, sometime sooner, theoretical physics will find the answers we seek. For the sake of our reality, we can only hope that it does. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. And we'll see you next time.